Good day, everyone, and good to have you with us today. And thank you for taking your time to participate in this webinar. My name is Patrik Andersson, and I'm a product specialist here at RaySafe. The content of today's webinar, we will start with an introduction of how the X-ray machine works and common hardware failures that can occur because of wear and tear. Then we will talk about why testing is important to ensure patient and staff safety. And the punchline for the webinar is that proper testing can be used for predictive maintenance to increase uptime and lifetime of the X-ray machine together with reduced dose to patients and staff. But why do we need to do QA measurements? Quality assurance tests are first done to establish measurements reference, and thereafter they serve to uncover possible malfunctions of wear and tear problems in the X-ray machine over time. As we will see, there are several problems that can occur in the X-ray machine which regular quality assurance testing can detect at an early stage. Malfunctioning of an X-ray machine is not only expensive due to new parts and downtime, it can also lead to increased dose to both patients and staff. And avoid unnecessary dose should always be top priority if one is working in accordance with the ALARA principle. Most of you are probably aware of this concept, but we must always have this in the back of our mind when discussing today's topic. In accordance with ALARA, one must always make everything one can to keep the dose as low as reasonable achievable. There is no known level of safe radiation, and the good of an exposure must always be greater than the potential risk of the exposure. Okay, time to get a little bit more concrete and talk about how change in output of the X-ray machine will affect not only the uptime of the machine, but also dose to patients and staff. Before we go into details on QA testing, let's make a recap and describe how an X-ray tube actually works. So the X-ray is made inside a vacuum container of glass or metal called the X-ray tube. The reason why it is vacuum is that electrons cannot accelerate in air, so it needs to be vacuumed. The X-ray tube has two crucial parts, the anode and the cathode. The cathode has two metal wires called filament, usually made of tungsten. When this filament is heated by electric current, electrons are released as a cloud around the filament. The difference in electric charge between the anode and the cathode makes these electrons accelerate towards the anode. When these electrons hit the anode plate, they stop very suddenly and transfer their energy to X-ray photons, which are emitted through the opening of the X-ray tube. For radiography, the anode is often also made of tungsten material to withstand high temperatures caused by electrons that hits it. The angle of the anode and the rotation makes the heat disperse on a larger area. The angle of the anode will impact the quality and the energy of the X-ray produced because it affects how deep electrons will penetrate the anode material and also the size of the focal spot where the photon hits the anode. An X-ray machine also need to have a beam restricting device in order to minimize X-ray dose and to improve image quality. The beam restricting device does that by limiting the X-ray field to the right size for the diagnostic procedure and by reducing scattered radiation. The most commonly used device is called a collimator. The primary collimator is located at the opening of the X-ray tube. The secondary collimator is placed inside a collimator house and has two sets of LED shutters that can be adjusted to make the X-ray field smaller or bigger in a rectangular or square shape. There is also a light bulb that illuminates the X-ray field to show its size and center. The light bulb must be mounted so that the X-ray field and the light field matches each other. There are several problems that are likely to occur with wear and tear in an X-ray machine. Every time X-ray is produced, the filament gets heated due to the current flowing inside of it. This heat may lead to evaporation, meaning atoms may disappear from the filament. The amount is usually extremely small, but with time, it will influence the filament thickness. And if the thickness changes over time, the current flowing inside changes since the resistance has changed. Modern machines will autocorrect for this by changing the voltage over the cathode. But with time, the filament will eventually break, just like a regular old-fashioned light bulb. Another phenomena that will occur with time is tube blackening. As atoms get vaporized in the filament, so are also atoms in the anode material. These atoms will be deposited on the inside of the X-ray tube, causing the glass to blacken over time. This will affect the qualities of the X-ray beam since the radiation will pass more matter and get shielded compared to clean glass. The anode itself will also suffer from wear and tear, not only caused by the vaporization. With use, it may become rougher, affecting the radiation quality. The photograph shows a well-used anode. The repeated heating and cooling has roughened the surface. It has also been exposed when not rotating, which has resulted in a local melted tungsten spot. The intense heating of this small area has in addition caused an expansion, which has resulted in a very tiny crack. If the anode then starts to rotate again, the crack may propagate and leading to a complete disc fracture. The roughening of the focal tract will cause a drop in the output and change in the radiation output spectrum. As the filament shape changes with time, together with anode wear and tear, the focal spot will also be affected. In general, a small focal spot is used when spatial resolution is important. A large focal spot will induce more photons per time, meaning that a shorter exposure time is possible. Also, larger focal spot is less sensitive to heat since it is spread over a larger area. Another thing to consider is the collimator light and X-ray field alignment. A reason for it to be out of alignment may be if the machine has received a blow, or maybe if it's handled roughly, making the lamp inside of it to shift. The light field from the collimator housing represents the area that is to be irradiated by the X-ray beam. If the X-ray field is not aligned with the light field, the operator may take a picture not fully containing the whole area, meaning another picture must be taken, which takes time and increased dose. There is also a chance that the operator takes a picture that is too big, which also leads to too much dose. Tube leakage is also another something to think about. The tube must be completely closed, and there should be no radiation coming out of it except through the exit hole. There might be design flaws making it not completely closed. There can also be a damage if it has received a blow or other type of rough handling. This was the end of the first part of the webinar. We have mainly focused on the X-ray tube or the X-ray tube hardware. We will now focus more on the softer and maybe more abstract parts, namely safety. But let's start with the concept of QA testing. We have earlier stated that the output of the machine can tell us something about the aging of it. Consistent output of the machine is important for the image quality and correct diagnosis while keeping the dose at a minimum, but also to uncover possible malfunction of wear and tear problems in the X-ray machine over time. But why do we need to do QA measurements? This is mainly driven by regulations to ensure patient and staff safety, but there are also some economical incentives. Malfunctioning of an X-ray machine is not only expensive due to new parts and downtime, malfunctioning can also lead to increased dose, both to patient and staff. And avoid unnecessary dose should always be top priority if one is working in accordance with ALARA. Making sure that the X-ray machine's outputs is consistent over time is of great importance if one would like to minimize patient dose. One should always strive towards getting a good image quality as possible without giving the patient unnecessary dose. The advantage of the exposure must be greater than the potential risk. Before we continue further with patient safety, I will linger just a few more minutes on the economical point of view. If one has a proper knowledge about the aging of the X-ray machine, one can easily plan for maintenance, heavily increasing uptime for the machine. If the machine unexpectedly breaks, it may take a long time for it to be repaired, and it will heavily affect the number of patients treated, and in some cases, also the income of the medical facility. Aging machine may also affect image quality. The worst case scenario is that the wrong diagnosis is made due to lack of information, but multiple images taken due to low quality also lead to higher dose to the patient and longer screening sessions. Longer screening sessions also mean fewer patients per day. Okay, we will now focus more on the safety bit of QA testing. All these hardware problems we have discussed also affect the output of the machine. And it is crucial that the X-ray machine operator knows the status of the machine. By knowing the status, the operator can give the correct settings to the machine, meaning a high quality picture can be taken while the dose to the patient is at minimum, all in accordance with ALARA. If it for some reason does not give the same output as before, it may have severe consequences which may affect patient and staff safety. Let's walk through some of the parameters measured during QA and try to understand how they will affect the machine output. Let's start with the parameter kV, or kilovoltage, a parameter affecting the image quality. The kilovoltage, or the kV, is the tube potential and is the energy of the electrons that are accelerating towards the anode. For use in medical imaging, the kV usually ranges between 20 to 150 kV, depending on the X-ray modality and type of diagnostic procedure. A high kV settings on the X-ray machine will produce radiation with high frequency, high energy, short wavelength, and strong penetration. And radiation with these qualities is referred to as hard X-rays. A low kV settings on the X-ray machine will produce radiation with low frequency, low energy, longer wavelength, and less penetrations. And radiation with these qualities is referred to as soft X-rays. A way to measure the kV is to measure the energy of the radiation. The photon spectrum contains energies between 0 to the set kV. If the machine is set to 120 kV, at least some photons should have that energy. And by looking at the highest energy photons in the spectrum, we can acquire kV, and we call it kVp, which stands for kV peak. There is a chance if there is a chance that the KV changes over time. It will affect the quality of the image taken. Most likely, there is something wrong with a controller inside the generator. They may also be worn out circuits, making it hard for the machine to ramp up the KV fast enough. A third option may be that there is a flaw in the actual power grid where it's installed. Milliampere, MA, is the electrical current flowing in the cathode filament. Since MA controls the number of electrons hitting the anode per second, it is directly related to the quantity of the X-ray produced. Milliampere second, mass, is the MA multiplied by the exposure time in seconds. The mass value determines the number of photons delivered during an X-ray exposure. There are mainly two ways of measuring mass. One can measure it invasively by hooking a sensor to the internal circuit in the X-ray machine. By doing this, one will measure a current corresponding to the same current going through the filament. The second way is non-invasively. Then one is measuring the electric field around the high voltage cables feeding the generator. There is also a third way, and it's to measure dose from the machine output. Dose is directly related to mass, but one can still not make too big conclusions since there are more parameters in place affecting the dose. By measuring dose, measuring dose can be a first easy step to get an indication of changed mass. If mass is changing over time, it will change the quality of the X-ray image as well. Most likely, there is something wrong with internal circuits in the X-ray machine. Thinning of the filament will change mass, but this is usually controlled by the X-ray machine itself. And another flaw may also be a disturbances in the local power grid. Half-value layer, or HVL, is a more abstract parameter explaining the machine output. One way to control the photon spectrum is by using filters. By adding filters, one will change the relationship between high and low energy photons. The best relationship between these two depends on modality, or which part of the patient is being imaged. One parameter used to explain this photon relationship is HVL, the half-value layer. It is defined by how much aluminum one needs to decrease the dose to 50%. More shielding will affect the HVL. A low HVL means a bigger share of low energy photons compared to a high HVL. And a change in HVL means a change in beam quality, which affects the X-ray image quality. There are mainly two ways of measuring HVL. The manual way is to first measure dose, then add filters until the measured dose is 50% of the original dose. These types of measurements are extremely hard to do, and the uncertainty is high. After the entrance of solid-state sensors instead of ion chambers, one has been able to get enough information out of one single exposure, so HVL can be calculated directly from just one single exposure. All previously discussed hardware defects will affect HVL. Filament and anode vaporization will add to the filtration. Roughening of the anode surface may also change HVL. We will now do a poll question to see if you have any idea on how a roughened anode surface may affect HVL. So the question itself is, how does roughening of the anode surface affect HVL? Is it A, it will decrease, B, it will increase, or C, depends on the anode material?
It looks like most of you have provided your answer now, but I will give you another 5 seconds before we close the poll. Okay, this is interesting. 50% of you have answered A, 30% that it will increase, B, and 20% have voted for C. So Patrick, I will hand it over to you to reveal the right answer and tell us why.
Thank you, Lena. This answer is maybe not that obvious. It's a bit of a hard question, to be honest, but the right answer is B. It will increase. And if we zoom into the anode surface, the left image shows an even anode surface. An electron is hitting it and penetrating a certain distance before it has converted all its energy to a photon. The photons must pass a certain distance inside the anode material until it gets out of the tube, meaning some of the photons are shielded by the anode itself. To the right, we have a rough anode surface. Since the surface of the anode is rough, the electrons will penetrate differently, and some electrons will converge to photons at the top of a roughness, while the rest will convert further in, making the photons travel different distances through the anode material before they exit the tube. A longer distance means higher filtration. A higher filtration means a higher share of high energy photons, meaning that the HVL will increase with a roughened anode surface. Maybe not the most obvious question. Dose. Let's continue with the parameter dose, which is a combination of kV and MA together with HVL, and it contains information to the image receiver. If you have a high MA and therefore a lot of photons, you will get a high dose. If you have a high kV, you will also get a high dose. If the information to the image receiver is perfect, a high quality image can be reconstructed by the computer while the patient has received minimum dose. If the information is bad, it will lead to poor image quality. And this may lead to faulty diagnosis and maybe more images must be taken. Since the dose is the product of all the other parameters, any X-ray machine hardware defect will most likely affect dose. By combining changes in dose, kV, mass, and HVL, one can make certain conclusions of the machine's status. Other types of measurements not fully relying on the beam quality is light and X-ray field alignment. If the machine has received a blow or such, the light bulb making the light field may be out of place. The operator should always try to make as small picture as possible to increase image quality and to minimize patient dose. If the field is misaligned, there is a chance that the operator takes a too small image, leaving out valuable information. If information is left out, wrong diagnosis may be made or more pictures may need to be taken, both affecting patient safety. If the picture taking is too large, patient has received unnecessary dose. And focal spot measurements can also be made to see if it matches the sizes given by the manufacturer itself. Making sure that the X-ray machine output is well known and consistent is of great importance if one would like to take a good quality image together with minimum patient dose. One should always strive towards getting as good image quality as possible without giving the patient unnecessary dose, all in accordance with ALARA. Unnecessary dose is given, for example, if there is too much low energy photons present that gets absorbed in the body and not contributing to the image. The image taken is not including the whole interesting area, or if the image taken is including more than the interesting area, or if the image quality is poor and more images must be taken. We will also talk about minimizing dose to staff. In most applications, staff is not close to the source when an image is taken. They usually leave the room or go behind some kind of shield. The patient always gets the highest dose during a procedure, but staff, on the other hand, are exposed to small amounts of radiation every day, and the accumulated dose over years can be quite high. It is therefore important to control the environment also from a staff perspective. When an exposure happens, it will be scattered radiation all over the room. If the operator is behind a shield, it is important to measure the efficiency of the shield. Also, the geometry of the room can give local hotspots of scattered radiation. If there is a tube leakage, a high energy unfiltered beam is propagating in the room, creating even more scatter, maybe behind the shield if you're unlucky. If the staff is outside the room, or if there is a busy hallway outside of the room, it is important that the wall is well shielded. Otherwise, staff and other patients may receive unnecessary dose. A usual way to shield a wall is by having lead plates inside of it. If the lead is damaged in any way, or if the plates have been poorly assembled in the wall, there might be radiation leaking out. One should therefore always do wall leakage measurements before commissioning and startup of the X-ray room. A special type of X-ray modality where staff is exposed to high doses is fluoroscopy. Fluoroscopy is a technique mainly used during surgeries. For example, during heart surgeries, the surgeon may insert the instrument in a blood vessel, guiding the instrument up to the heart through a blood vessel. But to be able to do this, the surgeon must know where the instrument is. By having a pulsed exposure with high frequency, one can follow what's happening inside the body in real time. Since the exposure time is seconds at a time, and maybe 30 minutes of total exposure time during the surgery, the energy of the photons must be much lower compared to regular radiography. Otherwise, the patient and staff in the surgical room will get insane amount of dose. But even though the energy is low, the procedure time is long. If the machine gives too much dose than required, the increased accumulated dose to the staff over years may be significantly higher. If there is something wrong and the machine gives a lot more dose than it should, it is also danger for the patient. Not does it only increase the long-term illness, It can also give short-term damages, such as burnt or dead skin tissue. Of course, tube and wall leakage in these type of rooms are also important, especially since the exposure time is so long compared to other modalities. We have so far talked about the X-ray tube and different hardware problems. We have also talked about why QA testing is important when it comes to uptime of the machine together with the patient and staff safety. We will now start to slightly switch focus to the actual testing and the products involved in testing. A few words about the tests themselves. The ones we display now are only a few tests that can be done. Exactly which tests are required differs from country to country. Even if countries have the same tests, they might have different procedures and acceptance criteria. It is therefore of utmost importance that one is aware of local regulations. Except testing regular parameters such as dose, kVp, and mass, and one can also test consistency and reproducibility of the machine. One is then doing several identical exposures, and the output must be the same. Luminance test is nothing that we have touched upon yet. This test is not related to the machine itself. Luminance tests are made on screens or monitors showing the X-ray image. If it, for example, it's too dark in certain areas, the wrong interpretation of the image is at risk. And one does not want the same image to look different on different monitors. Sensors used for medical imaging QA measurements have historically been different types of ion chambers. Using ion chambers made the QA procedure more complicated since they can only measure dose and dose rate easily. You had to do several different time-consuming measurements to receive kVp, HVL, etc. Not only is it time-consuming, but several measurement setups also gives higher risk for errors. On top of that, ion chambers may also be highly sensitive to variation in temperature and pressure. Since the entry of the solid state detectors, measurements have been more time efficient and accurate. You receive all interesting parameters in just one irradiation. You also do not have to worry about scattered radiations, especially when measuring with an ion chamber. Scattered radiation can make a big unwanted contribution, maybe up to 30% of added dose. Even though solid state detectors together with their integrated computational power are the best options for most QA measurements, there can be big differences between different detectors. The solid state detector has a certain energy dependence, meaning it can only interact with certain energies of the incoming photons. By putting shielding material with different thickness over the different diodes, one can create a system of diodes that can interact with the full energy spectrum of the diagnostic X-rays. The first diode has a small amount of shielding, or maybe none, and can only interact with low energy radiation. The second has slightly more shielding and can therefore only interact with radiation of higher energy, and so on and so forth. By having many diodes, you will also have many channels with information. By combining information from many channels, one can calculate a lot more from the radiation. For example, the amount of low energy photons compared to high energy photons. RaySafe has developed a truly unique QA system that can handle most or maybe all of your QA measurement needs. The main technology in our system is solid state detectors, but it does also contain a pencil-shaped ion chamber used for CTDI. Radiography and fluoroscopy are two often used modalities within diagnostic imaging. The X-tube RF sensor gives you all wanted parameters with high precisions for both modalities. It also has a small radiographic footprint, especially useful in fluoroscopy, where automatic brightness control, ABC, is used. Mammography is maybe the trickiest modality to measure on. The breast tissue is not that dense, meaning one must use low energy photons to get good images. Here one can see a typical mammography machine with different anode filter combinations. If we look at a generic photon spectrum in the top left corner, one can see some peaks and sudden drops that are material characteristics. By combining different materials, one can use these peaks and drops to construct an optimal spectrum for different types of breast. Not only does mammography machines have a much more complex photon spectrum compared to regular radiography, the small geometry and big variations in anode angles and materials between each machine makes it even harder to do proper measurements. The X2 mammography sensor, MAM sensor, can handle all kinds of difficulties occurring when measuring on mammography. What makes our product stand out is the ease of use. Even though mammography photon spectrums are complex and differs between machines, RaySafe has still been able to develop a mammography sensor with minimum number of settings. One can measure dose and HVL on all clinical mammography machines on the market without any settings at all. If you would like to measure KVP, apply a single setting, and then you are able to measure KVP on all diagnostic mammography machines on the market. The MAM sensor also has an increased window for dose, meaning one can use it for wide tomosynthesis sweeps. The simplicity is a unique feature for our X2 system. Our competitors requires a lot more settings for dose and KVP before a measurement can be made, and more settings makes it more complex with a higher risk of human error. Computed tomography or CT machine uses a thin beam that rotates around the body. To be able to measure dose properly, the sensor must be able to pick up radiation from the whole 360-degree rotation. The CT sensor is a pencil-shaped ion chamber used during some types of QA measurements. Since it's an ion chamber, it will pick up radiation for the full 360-degree rotations of the X-ray tube. The sensor itself is an ion chamber with an electrometer built into a compact unit. It has a built-in pressure sensor and a thermometer. This gives us a signal that is automatically temperature corrected for the air temperature inside the ion chamber and not inside the room. All sensors are connected to the X2 base unit through USB cables. All parameters are easy to see on the big screen, and one can look at waveforms and make waveforms analysis directly in the base unit. The base unit also includes a mass sensor, meaning no additional external mass sensor is required. We have, of course, other products in the RaySafe portfolio that can help you conduct a full-scale QA measurements. Our X2 light sensor is for checking monitors showing the X-ray image, making sure they have the right luminance. The XR Plus is our ruler that can help you with the light X-ray field alignment. We also have different types of pinholes and slits, checking the focal spot sites of the X-ray machine. Of course, we have products with focus on radiation protection as well. The X2 system has a survey meter, A perfect meter when it comes to measuring scatter or tube leakage from diagnostic imaging machine. But I would also like to promote the RaySafe 452. This is our newest product in the RaySafe family, and it's a versatile survey meter with a huge application range. Not only is it perfect for scatter in tube leakage measurements, but it has a much wider energy range, making it an excellent option for higher energy photons applications such as radiation therapy or linear accelerators or LINEX. It can also be used as a contamination meter, which is of great help at radiotherapy clinics. Our real-time dosimetry system, I3, is also a great product when it comes to decreased dose to staff during fluoroscopy. A dosimeter is placed on the staff in the operating room. By giving staff instant visual feedback on the received dose during the exposure, they can make immediate actions and change working procedures to lower their dose. Finally, we would like to conclude this webinar by just a few words about standards. QA testing is regulated by law to ensure patient and staff safety. Regulations differ depending on country and sometimes even regions. It is therefore of utmost importance that the medical physicians, radiation officer, or whoever is in charge of these questions at the hospital is well informed about regulations. If the regulations is not specifying a certain method on how to do certain measurements, the same person must create this method him or herself and make certain that the regulations are fulfilled. Okay, that was the end of this presentation, and we will now have some time for questions and answers. And Lena, do you know if we have received any questions for us today?
Yes, we have received some very interesting questions from the audience. Let's see. Yeah, you said that measured mass is a corresponding current. It is not the actual current going through the filament?
Yeah, that is true, at least on more modern machine. On modern machine, you hook up the mass sensor and you are actually not measuring the exact same current that going through the filament. You are measuring a corresponding current. On older machines, there might be, or it might be the same current. That is actually more of a design questions of from the manufacturer.
Okay, thank you. You mentioned that the CT sensor can temperature correct it depending on the temperature inside the ion chamber, not the room. When is the temperature inside the ion chamber and the room not the same?
Yes. I would say this is mainly when conducting the CTDI measurements. When you have the CTDI measurements, you have this huge PMMA phantom, this huge plastic phantom which you insert in the CT machine, and you also insert the ion chamber inside this phantom. And for example, if you have left the phantom in your car and it's been a cold night, the phantom may have a much lower temperature than the actual temperature inside the room. And if you then insert the ion the ion chamber inside this cold phantom, you will not have the same temperature inside the ion chamber compared to the rest of the room. Or if you example, if it's the same problem if you are in a warm country, maybe you forgot your phantom in a warm car for a couple of hours, and then you take it inside into a cooler examination room. then of course the ion chamber will get a lot more warmer because of all the heat inside the phantom. And it will take quite many hours for the phantom to receive the same temperature as the room or the ambient temperature. But this is not an issue if you have the X2 CT sensor because it's correcting according to the temperature inside the ion chamber.
Okay. So what is the content of the commissioning report for room/machine?
Sorry, could you please repeat that?
What is the content of the commissioning report for room/machine?
Oh, it depends, I would say, also on local regulations. The content, it should, of course, be the tube leakage and the wall leakage, and it's so hard to say. It varies so much depending on country and so on. So I'm afraid I cannot give you a straight answer or an easy answer to that.
Okay. So can you tell an example of where the same type of measurement differs between countries?
Oh, there are a lot, of course, but just a thing on top of my head here is mammography measurements, for example. When you do certain QA measurements and you would like to measure dose on mammography machines, according to international standards used all over the world, except in the US, you need to place for example, the sensor 6 centimeters from the chest wall and elevated 4 centimeters, if I remember everything correctly. There is the place where you should place the sensor during those measurements. While in the US, when you do the same type of measurements, you should place it 4 centimeters from the chest wall and elevated 4.5 centimeters. I hope I got those numbers correct. But it's at least it's an example of where it differs.
Okay. So in my country, I do not believe there is any specific regulations. What do I do?
Yeah, what do you do? There are, of course, international standards which are useful as guidelines when doing QA measurements and creating methods. But it's the country where you are working are in charge of the regulations. So even if you're following international standards, it's the country itself who must make the call if you are fulfilling the regulations or not. So you cannot just take an international standard and following it and believe that everything is working fine. You need to, I guess, the country itself need to work harder on these type of questions and finalizing regulations.
Okay, so does the X-ray tube age by not being used for many years?
It depends. We have mainly spoken, or earlier we spoke of aging when the machine was used. And if it's not used at all, let's say that it's been standing still for, I don't know, many years, locked in a room somewhere, some things can happen and other things cannot. If we start by looking at the X-ray tube itself, then nothing can actually happen at all with time because everything is in vacuum. And if nothing has nothing has been used, then has been no evaporation and there is no atmosphere oxidizing any material such. But filters that is placed outside of the tube itself may age by time, mainly due to oxidation of with air in the in the atmosphere. But this is highly material dependent. Most filters are quite insensitive to this type of corrosions. Other materials may be more used in mammography machines. For example, silver may absolutely oxidize and age with time.
Okay, so this will be the last question for this webinar. No, we do have two here still. The X2 is lead back, so do we need any additional precautions for minimizing scatter from underlying surface to our measurements?
That's a good question. It doesn't actually have a lead container, a lead back. It's a tin cage, so the diodes are inside a tin material, which is also an excellent absorber of scattered radiation. And no, there is really no other precautions that must be done, because the efficiency of this tin cage, it's good. It would only, I don't know if it's less than a percentage or something like that, that is going through this tin cage. So it has an excellent backscatter protection.
And this will be the final question then. Can we expect any variation between measurements depending on the time of the day? Tube loading, that's within brackets.
Oh, well, in an ideal system, I would say no. But of course, we are never in an ideal system. If we have, as I mentioned before when we spoke about kV and mass, the local power grid can of course affect the machine's possibility to ramp up mass and kV. And let's see, if you are in an area where there is a big usage of energy at certain time points, that may affect the local power grid, making it harder for the machine to ramp up. Hopefully, the hospital or the medical clinic facility has a stable power grid, so hopefully it's not a problem, but it can be.
Okay, that was the end of the list of the questions that we received. And thank you so much for sending your questions. It's great.
Thank you so much.
So I believe we need to wrap up now.